All right, let's jump right into this explainer. In the fast-moving world of AI news, we are constantly tracking how the industry is trying to solve the massive GPU memory bottlenecks created by long-reasoning AI models. Today, we're looking at a genuinely fascinating, newly proposed solution called Kara, which fundamentally rethinks how we handle model memory during extended inference.
We've got a packed roadmap today. We'll start with the KV cache memory monster, see why static compression fails, introduce Kara's sliding window approach and pipeline, and finally cover VLLM integration and real-world deployment impact.
Section 1. The KV cache memory monster. This is literally the cost of thinking longer. We have to start by establishing the villain of our story, the rapidly growing key value cache, which silently devours our system memory the longer we ask our AI models to quote-unquote think.
You see this with the latest reasoning language models, right? They generate this extended chain of thought sequence before ever actually giving you a final answer. But that extended decoding phase has a major hidden cost. Every single generated token appends a brand new KV pair to the cache. And because this cache grows linearly with the sequence length, the model's attention mechanism is forced to process an ever-expanding matrix of past states.
Just as a quick refresher, the KV cache is absolutely essential for saving compute time. Without it, the model would have to recalculate attention for every previous word from scratch for every single new word it generates. No way we could do that efficiently. But unfortunately, in these long chain of thought sequences, storing all those previous token states just eats up massive amounts of GPU high bandwidth memory. This accumulation directly increases your decoding latency and strictly caps the number of requests you can process at once.
Moving right along to Section 2. Why static compression fails. The rigid boundaries of our current fixes. To fix this severe memory bloat, engineers use cache compression, but the current generation of threshold-triggered policies have some pretty glaring structural failures.
Existing compression methods try to drop or merge unimportant KV pairs. However, they rely on static, threshold-triggered policies. They basically look at an attention score, compare it against a fixed hard-coded number, and just cut whatever falls below it. These older methods act like a rigid cookie cutter. They either fail to prune enough data to actually fix your throughput bottleneck, or they drop pairs way too aggressively. When entire blocks of a sequence get eliminated blindly like that, the model loses vital structural context, which leads directly to information loss and degraded reasoning accuracy. Important semantic context simply doesn't fit into neat, fixed-size chunks.
So it's a stark contrast. You've got the old way, rigid boundaries resulting in stagnant throughput. And then you've got this paradigm shift toward a dynamic sliding window approach that evaluates context locally and intelligently.
Which brings us perfectly to Section 3. Enter Kara, sliding window compression, a dynamic solution for dynamic reasoning. This is the hero of our tech journey today. Kara is a newly proposed compression method that completely abandons those static thresholds and operates exclusively on recently generated context at decoding time.
Instead of blindly enforcing a global cutoff across the entire prompt history, Kara acts more like a flexible spotlight. It evaluates the relevance of context dynamically as the sequence extends, tracking only the most recently generated tokens within a localized sliding window. Older context outside this window simply remains uncompressed unless the underlying memory manager actively evicts it. This completely prevents that catastrophic information loss we saw with the old static block elimination.
Section 4. Kara's three-stage pipeline. Let's look at how this sliding window actually operates under the hood. The crucial point here is understanding how this compression happens seamlessly during the decoding phase. It all executes in a neat three-stage pipeline. First up, it uses bidirectional attention scoring. Standard autoregressive models only look backward, right? Well, Kara cleverly applies bidirectional attention within its sliding window. This means it evaluates token relationships in both directions to find semantically dense regions. Second, it selects a subset of highly informative pairs based on their contribution to future token predictions. And third, it pushes these pairs into a token-to-chunk expansion module.
This is where the magic really happens. Instead of keeping just isolated tokens or forcing data into rigid blocks, token-to-chunk expands the selected high-value KV pairs into flexible-sized semantic chunks, and it can do this at arbitrary token positions. This means the system easily preserves contiguous context boundaries across highly variable length reasoning steps.
Okay, Section 5. Integration with VLLM page detention. Bringing Kara to the serving layer. Because let's be real, a great compression algorithm is completely useless if it doesn't integrate with open-source infrastructure, specifically the highly popular VLLM engine and its paged attention memory manager.
Page detention revolutionized serving by treating KV caches like virtual memory in an operating system, using non-contiguous blocks of physical memory to stop fragmentation waste. Well, the researchers behind Kara built a framework called KV-LLM directly on top of VLLM to take advantage of this. KV-LLM intercepts the page detention scheduler. It dynamically allocates reduced KV cache blocks based on Kara's sliding window compression ratio and routes those compressed blocks through standard virtual to physical memory mapping. And the best part? It maintains total backward compatibility with standard VLLM APIs and OpenAI-compatible serving endpoints.
Because this entire process happens purely at inference time. Right at the serving layer, you don't have to retrain your model weights at all. You don't have to modify your attention heads. You can take an existing open-source reasoning model, plug it into KV-LLM, and immediately start realizing memory benefits without an expensive fine-tuning phase. It's a real game changer.
Section 6. Deployment and Serving Impact. Here is what developers actually need to know about the practical realities and impacts of deploying Kara in your own stacks.
The deployment steps are remarkably straightforward. You deploy KV-LLM just like you would a standard VLLM server. From there, you configure your sliding window sizes and compression thresholds via server-side parameters, carefully tuning them based on your specific model's attention patterns. You'll want to heavily monitor your KB cache utilization during load testing and absolutely verify that the token-to-chunk expansion is preserving your reasoning accuracy. And a huge pro tip from the documentation: always pin your framework versions in your deployment manifests. This cache compression logic is evolving rapidly, and unverified updates can drastically alter your memory allocation behavior overnight.
When properly tuned, the system impact is striking. By compressing only the active decoding window, KV-LLM frees up massive amounts of high-bandwidth memory. This significantly lower memory footprint allows you to pack in way more batch requests concurrently. More requests in the batch directly drives up your overall output throughput, making your very expensive GPU hardware far more cost-effective. However, there's always a trade-off, right? We need to be aware of the latency side of things. The bidirectional scoring and token-to-chunk expansion do introduce a minor compute overhead during the decoding step. On short context workloads, this computation overhead might actually outweigh the memory compression benefits. So you really want to strictly reserve Kara for those massive chain-of-thought reasoning models where cache bloat is the primary enemy of latency.
I want to leave you with this provocative thought to ponder. Kara is an incredibly elegant software solution to a hardware problem, but as our AI models are asked to think for longer and longer periods, generating thousands of reasoning tokens before spitting out a single output, is dynamic cache compression the ultimate answer, or are we just temporarily delaying an inevitable collision with hardware physics? It's a fascinating space, and understanding these memory management innovations is absolutely crucial for anyone building the next generation of AI applications. Thanks for joining me on this explainer. Keep exploring, and I'll catch you next time.